In this tutorial, you will learn to use Epsilon Poisson Solver. Epsilon Poisson Solver is a filter that can be applied on Epsilon data, and basically it is used to perform an analytical or numerical solution of the Poisson equation that's related to the vortex drag or induced drag. So let's take a look at that in detail. So Epsilon Poisson Solver is a specific filter that can only be applied on Epsilon data. Basically, it solves the Poisson equation for multiple cases. The first case is the Fourier solution, and that concerns most of the CFD applications where you actually simulate the flying object far from the surface. In that case, you just take a slice of the domain. That plane you have the vorticity, and based on the mass scale equation or the weight-reduced exergy approach, you can actually compute the vortex drag or the induced drag starting from this actual vorticity, and this requires solving Poisson equation. That the output is a stream function. The stream function basically can be visualized as the streamlines lying on that plane that are associated to the rotational velocity of the flow field. This solution is, first of all, provided for Fourier solutions, but you can also solve this Poisson equation in constrained flows, that is in a wind tunnel. In fact, what you're seeing here is the wake of a wing and nacelle aircraft, and these are the boundaries of the wind tunnel. And what you're seeing here in red, green is actually the stream function at that survey plane that has been computed by solving the Poisson equation that is driven by the actual vorticity shed by the object. You can actually solve the Poisson equation also in ground effect. That's a particular case of the bounded flow. And we will see that in detail how it works, but basically, again, we start from the actual vorticity shed by the object, and taking into account the presence of the floor, we can compute the entire Poisson equation on the entire domain or inside the wake. And this approach allows you to perform wake-reduced solutions. You can either solve the Poisson equation at the entire domain, at the entire survey plane, or you can just solve the Poisson equation inside the wake, which is faster, and it also allows you to separate different elements of the wake, which allows you to perform vortex drag analysis to understand where vortex drag is being generated and what you can do to reduce vortex drag. So, Epsilon Poisson Solver, as I told you, is a filter that is applied to Epsilon data. And in order to understand what are the steps that have been made in order to achieve our objective, we have to understand first what's the data I have from Epsilon data. In my case, I have to take, first of all, the grid, the BTK and structure grid, because this is the geometrical information that will be used to generate a slice of the domain to compute the Poisson equation at each point of the desired plane. Then, of course, I will take some point data like a vorticity vector, because, of course, vorticity drives the Poisson equation. I need this information, as well as some point coordinates and other arrays. So, with that in hand, let's see what is inside Epsilon Poisson Solver and what happens on the background inside ParaView each time you execute Epsilon Poisson Solver. Well, the first step is obviously to load the input data. Basically, I get the point data and the field data coming from Epsilon data, and then I generate a slice of the domain, or you can get the slice if it's actually being generated in Epsilon data. So the idea is basically to take the survey plane data, because we can only solve 2D Poisson equation lying at the survey plane. We cannot, at this stage, at this version of Epsilon v3.0, we cannot solve the 3D Poisson equation yet. So we are just limited to 2D planes, the survey plane, but this is quite practical for your analysis. So once I have the data in hand, I can tackle the cell-based calculations. This is actually the Poisson equation that I have to solve, which is driven by the actual vorticity. This is the classical mass scale equation, and you will find the same with the weight-reduced exergy formulation. And there is an analytical solution for this equation given by this expression where you have the stream function at each point of the domain, which is basically an integral of a green solution, which is coupled to the axial vorticity. And these quantities are integrated on the entire survey plane S out. And as you can see, this equation requires dealing with point data marked as YZ. These are the point coordinates at the survey plane. But you also have to deal with cell data marked with the subscript C. It requires the coordinate YC, ZC, but also the surfaces of each cell at that survey plane. So one of the operations that I have to perform inside the Python filter is to convert the input point data coming from Epsilon data to cell data, because I really need this to compute these terms here. And of course, this requires obtaining the cell centers for this operation to compute the vorticity at the cell center. And I also need the cell area to compute this part of the integral. And of course, these are all BTK operations. And again, if you want to improve the code, you want to adapt it to your needs, you can still access to the code and modify those BTK operations. And the next step is to compute the singularities method. In fact, there are several methods to solve the Poisson equation. For the case of wind tunnel testing, I will use this method, singularities. Let me show you how it works. Let's consider a wind tunnel here. You can see just the outline and the transparency of the walls of the wind tunnel. You can see a wing here, that's the body that's being tested, and this is the wake. This is data that you can gather typically in a wind tunnel, either by PIB or 5-hole probe. And the idea is to generate a panel method at the boundary of the wind tunnel lying at the survey plane position. And all along this line, you generate a sort of paneling, and each side, at each one of these panels, you have to define circulation, and you check that at each control point, the normal velocity associated to the velocity induced by these singularities distributed on the entire surface, plus the velocity induced by the vorticity distributed wake, must give a normal velocity 0, which is the non-penetration condition. So with this information in hand, you can solve a linear matrix solution that will give you the intensity of gamma at each one of these wall panels, and this will give you the distribution of vorticity of circulation at the wall that allows you to deform the stream function and taking into account the presence of the wall when you try to compute the vortex drag. So once we solve the linear matrix equation that gives me gamma, I generate a background grid inside all along the wind tunnel cross section, and each point of this grid I compute the stream function based on the equation that I presented you before. Once I'm happy with that, once I'm happy with that the stream function actually follows the wall as it is expected, I can go to the next step, that's actually computing the stream function inside the wake. That's my measure objective, because I really want to compute vortex drag, and vortex drag is only a wake reduced parameter, which requires to compute the stream function at each point of the wake that has been measured during the wind tunnel run. And of course, these are all BTK operations that are embedded into the Python code. The other approach that you have to solve the Poisson equation is by using green functions. Green functions basically start from your Poisson equation that I have shown you before. And this is a solution that I showed you before, the solution that uses these green functions. Basically, it requires that this function be evaluated at each point of the wake. For example, typical CFD approach when you study an aircraft or other type of bodies is to analyze just 1/2 of the geometry. So in some cases you study the entire body, sometimes you study half of the body, and depending what are you simulating, the green function will change. So I will show you all these cases. For any case, independently of the case of the type of geometry, what you do is you start from the vorticity, actual vorticity at each point of the wake, and you solve this equation using these green functions to compute at point by point the stream function as you see here below. So let me show you how it's computed for each case. And that's what I call green function combinations, because the green function will change depending on the case. The first case that I will cover is the free air full model. That is, let's say that you have performed a CFD simulation of the entire object. So you actually have the entire wake simulated. And in that case, you should have to apply this green function. As you can see here, this is the analytical solution of the Poisson equation, as it was provided by Pascal. This equation will be the same, but it will be repeated either by multiplication or by division, depending on the geometry. So let me show you the other cases. For full free air full model, that's all. It is the equation that it is solved inside the Python code. But if the geometry gets more complex, the green equation will be more complex. So for the case of free air half model, that's the more typical CFD approach. This is the case. You have half of the body and half of the wake. You have to reproduce the lacking part, this part, introducing a mirror data. Of course, you don't want to generate a mirror of the entire 3D information or even the wake, the 2D wake. You don't want to generate a mirror. Because there's a smarter way to do that is by generating a mirror green function. So you stick to this because this is what you have simulated, and instead of mirroring the actual data, you generate that mirror analytically by mirroring the green function. So this is all performed internally inside the code. You don't have to worry about, but you really have to keep in mind that each time you execute Epsilon. For the other case, that's ground effect with the full model, that is this case, where you actually have simulated the entire geometry and you have access to the entire wake, but you have ground effect. In this case, the presence of the wall introduces changes, and that means that you have to introduce its mirror. In this case, there is no physical mirror, but again, you have to introduce the numerical mirror by using a mirror of the green function, which means dividing the green function that I showed you before by the same quantity corresponding to the mirror. This is all achieved inside Epsilon, and you don't have to worry about. The fourth case is still ground effect, but the half model, that is this one. Where you have the ground here and you have the symmetry plane here. You should have simulated this quarter part, that is half of the body. You should have access to half of the wake. So in this case, you have to generate, first of all, the mirror of the geometry, and afterwards, the effect of the wall. And this is achieved mathematically by adding extra green functions. And again, all this is achieved internally inside Epsilon. You don't have to worry about that. Then for the case of wind tunnel testing, you have two cases, of course. You have full model, the first one. And in that case, let's say this is the wind tunnel boundary. And this is the actual model that you have tested. In order to take into account the presence of the wind tunnel walls, you have to introduce a series of layers. This is the first layer around the body that represents the mirror of each one of the walls and each one of the mirror of the walls. But unfortunately, adding one layer of mirror is not enough. You have to add several amount of layers in order to obtain a proper Poisson equation solution, which is quite demanding from a numeric point of view. And that's why for wind tunnel testing, it is far faster to use this singularity method. And this is the preconized. I really strongly recommend you to use first this method. Just to verify the solution, you can actually use green function for wind tunnel testing, of course. The other case is wind tunnel testing with half model. This is your wind tunnel walls, this half model that you're testing. And as before, you have to introduce the presence of the wall numerically. So you introduce a mirror of each one of the walls. And as before, you need to add several layers. And it's the same as the full model. Basically, singularities method and green functions are the two approaches that are actually coded in Paraview. In older versions, you have the iterative solver, And this is well known because basically you start from your Poisson equation. Basically, what you provide is a solution based on finite differences. This is the same equation discretized. It requires an iterative numerical solution. Basically, you start, let's say this is a wind tunnel. This is the entire cross-section of the wind tunnel, and you generate a uniform reference grid that is initialized everywhere with the string function, local string function value at 0. And then by solving the equation in an iterative manner, you can actually achieve a converged state. But the problem of this approach is that it required a uniform grid, because this method will only work with a uniform grid. And it's not that accurate. You have to control the convergence. And in particular, when you analyze wake data, you have to deal with a lot of concentration of points in the wake region. You don't want a uniform grid. You want really a very dense grid in the wake region. So this method is not well suited to cover those cases, and that's why this method is not very practical, and that's why you have deprecated. It is no longer available in Epsilon V3, despite it has been used before. Well, at this point, we have solved the Poisson equation, and now we are ready to compute vortex drag or induced drag. So this was our starting point. We have started trying to solve the Poisson equation starting from the vorticity. We have achieved that. We managed to compute the string function that's given either by the singularities method or the green function. Now that I have that in hand, I can keep going and compute vortex drag. This is the vortex drag given by the wake-reduced exergy method, or it's quite similar to the Maskell method. And basically it requires integral all across the wake cross-section of the string function that we should have computed and the actual vorticity. These are the two parameters that you really needed. So with all that, you can compute vortex drag density at each point of the wake, and then by integrating, you obtain the vortex drag. If you take a look at the Maskell equation, you will see that there is an extra parameter in the most general equation. Vortex drag is given in part by the actual vorticity and in part by other term that it is associated with transverse flow. This term is associated to the rotational flow field, which is more intuitive, and this term is related to the transverse flow field. You can take a look to the theoretical background tutorial series to understand better this. Now I should be concentrated more on the what are the operations behind the filter itself. Just a quick review of what it is. Basically, this phi is a potential function that comes from this equation that is driven by this term sigma, and sigma is nothing but the transverse flow gradient. But I'll let you discover on the theoretical tutorial series. Now, just go straight to the point, and after computing vortex drag, we are ready to output this data, and this is achieved as a BTK poly data. Well, all the features that we have discussed before are actually present at the interface. So in the next part, I will tackle a live demonstration of this filter so you can be more familiarized with all the concepts we have discussed previously in this presentation. Well, for the practical part of this tutorial, we will use open data available at our website. So go to our website, open data, CFD data, and then if you scroll down, you will find this case, the 3D subsonic case. It is a rectangular wing at an angle of attack of 10 degrees and Mach number of 0.3. We'll try to compute the Poisson equation at a given survey plane position, something like this. I'll let you download and execute Epsilon in your computer. I have already downloaded the case, I executed Epsilon aerodata, and I also extracted the body surface by using Epsilon nearfield, and now I'm ready to apply the new filter. Be applied on Epsilon aerodatas, so be sure Epsilon aerodata is blue, which means this is the active element inside Paraview. And then you go here to Epsilon Poisson Solver and just click on there. Be sure that this tool here, the apply changes automatically, is not activated. It must be gray. If it's dark gray, it means it's activated, and it's not recommended because it's quite annoying. So, first thing first, Epsilon Poisson Solver is supposed to solve the Poisson equation at the solver plane. It's a 2D Poisson Solver equation. Since loading this case, a 3D case, may require some time and a lot of memory space, especially when you execute Epsilon arrow data, you have to consider the possibility that a parabolic crashes. It has some stability issues that you have to take into account, so I strongly suggest each time you advance in your analysis to make intermediate saves. There are two options. Let me first delete this. The first option is to save state. So go see here, independently what you have done here, you can save all these steps so they can be reproduced automatically when you open specific files. So go to File, Save State, and then you save, you put the name that you want in the path that you want, and we'll save a PBSM. That's a sort of journal that basically, when you open this PBSM file, will reproduce all these steps, including all the parameters that you have defined. This is a way to save what you have done. In this particular case of Epsilon Poisson Solver, we will use another approach. I will go to Epsilon arrow data, and first of all, when apply Epsilon Poisson Solver, the first thing I will do is to, if you have a 3D CFD case, you have to perform a slice of the input data. Then you have to precise the position of the solver plane. I will put that, let's say, almost one core downstream. And let's apply as default. Basically, it generates a solver plane downstream of the body. This basically has taken the entire 3D domain. It has been sliced at the desired position. And the solver plane is normal to the upstream flow direction. You can realize that the plane is not aligned with the normal of the surface. It is a little bit inclined, and that's because the upstream flow direction follows the X aerodynamic axis. And at this plane, generated by the Poisson solver, you have all the parameters computed by Epsilon arrow data. Let's use, for example, the energy to visualize the wake. Epsilon Poisson Solver might induce parabolic to crash in some heavy calculations because solving Poisson equation is quite heavy, it's quite demanding. It may require sometimes 10 minutes or sometimes 15 minutes, depending on the density of points inside your 3D grid and depending on the method you use. So you have to be prepared for that. And what I used to do in order to deal with that is to save this slice of the 3D domain, because let's say parabolic crashes, I will have this slice already prepared, so that simply I have to reload the slice of the domain and I apply Epsilon Poisson Solver on that slice. That being the best approach, I will explain how to save this solver plane. There are two ways. The first way is here in advanced options inside Epsilon Poisson Solver. You will have an option to save the data in BTP format. You just have to define the path and the name of the file of the output. The other alternative is to select here the element that you want to save and click here, Save Data. We will pop up this interface. You have to define a specific name, let's say independently. You can choose different types of output format. You can use either BTP or BTK independently. I don't care. I will put slide plane 3D. So I will say that in my desktop, just in case parabolic crashes. So I have the slice I want to analyze. This is the plane where I want to actually solve the Poisson equation. So having said that, let's go and tackle the Epsilon Poisson solver. So at this point, I have generated my backup slice of the 3D domain, and that's the file I want to modify and to compute the Poisson solver equation. So let's hide the current Poisson solver, and let's open the solver plane, the slice plane 3D that I have generated. As before, it will contain all the parameters. I will visualize the wake with energy. Now I can apply Epsilon Poisson Solver. So let's go for it. In this case, I have two options. Either I can solve the entire Poisson equation on the entire survey plane, or I can solve the Poisson equation just inside the wake cross-section. Usually you should analyze the wake cross-section because Maskell method or the wake reduced exergy method will require only wake data. So it's useless to analyze the entire domain because it will make the process more slow. But what I suggest you, what I really recommend is to solve first the Poisson equation on the entire plane because you might visualize the entire stream function. You check if the stream function has been properly computed. In the case if you really want to compute just inside the wake, use this option, clip by scalar. And you have to select a given clip parameter to take away the wake. For example, you can take a vorticity magnitude because at the end of the day we're using vorticity to solve Poisson equation. Let's use a given threshold value, something like this, and it should take the wake was too large. Okay. This is a clip parameter. I select a parameter to identify the wake. In my case, I use the vorticity magnitude, and I define a threshold value to clip away the clip. If the wake is not being selected, if you are getting the external part of the wake, you have to click here in invert clip. It will retain the remaining part. By default, it works fine usually, but if not, that's not the case, just go and click on invert. So this is the step that we'll analyze afterwards. In the first step, I will analyze the entire plane. So let's go back, and this is the entire plane. So now we have seen these two options. Now we can tackle the Poisson solver. The first two options were just data pretreatment to generate the slice of the plane and to take away the wake. But what we really want to do is to solve the Poisson equation. So the first part is to define the flow domain. In my case, it's free air. You have all the options that we have discussed before, free air or wind tunnel. This is a CFD simulation of a free air case, so I let it as it is. Then inside free air, you have options like full wake, symmetry plane, or well at some specific positions. In my case, I have simulated just half of the body with the symmetry plane lying at the XZ plane. So here I have to say that I have symmetry plane at the XZ plane. And I can even define the coordinate, the y coordinate of the symmetry plane or the wall. In my case, it's 0 because the symmetry plane lies at the 0 y coordinate, so I let it 0. Then for free air, you don't have choice. You can only solve the Poisson equation by using the green function. That's why it's light gray. You cannot modify this parameter. For the case of wind tunnel, you have two options, green functions and the panel method. But for free air, it's just green functions. Inside the other options are velocity potential. If you want to compute or not, remember that the Maskell equation allows you to include an extra term. So you can do not compute that. That's the option by default. Usually it's not required to compute vortex drag, but if you really want to include the effect of the transverse velocity field, you can choose any of these two options here. I let it by default without its computation because it will duplicate the time to solve the Poisson equation, in fact. And the last option, it allows you to select the action to perform. The first option is to visualize the symmetry plane. So if we apply, we will see a line that lies at the symmetry plane, if you see that in the front. This shows you, allows you to confirm that you are actually placed correctly, the symmetry plane. It's just for that. And then you just have to solve the Poisson equation. When you select this option, just take into account that this operation might take several minutes. In my case, it will take about 5 to 10 minutes for this entire slice of the domain, and that varies from one computer to another. So I click on apply and I wait some minutes. I will go back to you. Well, the calculation has finished in my computer. If you see here in the output messages, you have some statistics. In my case, it has taken almost 7 minutes to complete. And again, that might change from one computer to another. The first thing that you will realize here is that it computes the vortex drag. In my case, it's almost 280 drag counts, which is correct for this wing. And if you go to the survey plane, you will see that the output of Poisson Solver is the stream function. The stream function you have here, psi. And as you can see, it has been solved on the entire survey plane. And also, you have to verify that the stream function reaches the value 0 at the symmetry plane. That's my case, so that's good. That means that the equation has been correctly solved. And then the value of the stream function might be positive or negative depending on the sign of vorticity. So don't be scared if sometimes you have a negative stream function. What really matters is the product of the stream function and the vorticity that must be locally positive, because that gives you the vortex drag. In fact, you have here in Poisson two options. C is the stream function itself, and also you have the actual vorticity x. And again, it is the product of both fields. This field, the vorticity, and the other field, stream function, that gives you locally at each point the density of vortex drag according to the Maskell method or the weight-reduced vortex drag calculation. And this can be found here. If you go to Maskell vortex drag, you will see that at each point of the wake, you have the vortex drag density. And you can change that scale to visualize that better. You can see that it actually occupies the entire wake, especially at the vortex core. And this is the quantity at the entire survey plane that has been integrated that gives the vortex drag value of 279 drag count. So that's all for a 3D case. Of course, we have solved the Poisson equation at the entire survey plane, and that's why I have taken 6 minutes. But we can do the same just by analyzing data at the wake only. That will take some few minutes less, let's say 4 minutes or so, or 3 minutes, simply because on the entire survey plane, the majority of the points lying at the survey plane are concentrated at the wake. So even though if you analyze just the wake, it will take a relatively long time to compute. So that's normal. All the Poisson solvers take a lot of time. Okay, that's all for the case that we are studying right now. That's a free air with a symmetry plane at the XZ plane. For the case of ground effect, it will be exactly the same. In this time, you will have just to define, for example, the symmetry plane. Let's say this is a wing flying close to the ground
lying on the XY plane, somewhat down below. In that case, you have to define here the wall at the XY plane, and you have to define the set coordinate of that plane. That's all, and then you execute again, and that's all. But now we'll try to tackle the wind tunnel approach. Let's consider that this wake that we have here actually corresponds to a wind tunnel testing. So first of all, I want to clip by scalar because that's what's actually happened in the wind tunnel testing. So this is normally what you get after a wind tunnel testing, either by PAV or 5-hole probe wake survey. You just have the wake data. And inside the wake, you have multiple parameters. Of course, after passing through epsilon data, you will have quantities like energy, for example. But usually you should have just the velocity, vorticity, and so on. So the idea is to compute the vortex drag in a wind tunnel environment. So let's suppose that this is the actual wind tunnel model. Let's suppose this is the wake that we have measured. We'll try to implement the solution of the Poisson equation for a wind tunnel testing. So you have to change here a flow domain to wind tunnel. And when you select wind tunnel, you have to define the boundaries of the wind tunnel. So we have to draw a sort of wind tunnel. In my case, I will put it between 0 to 2 meters along the span, minus 1 meter plus 1 meter on the z direction. and display tunnel walls. So what I have here is the wake that it is the actual input. Let's say this is what we have measured. And this is the tunnel boundary at the server plane. We'll change and increase that a little bit more. Let's say 3 meters span. Okay. Now the idea is to solve the Poisson equation on this wind tunnel cross section. And in order to achieve that, we will use the singularities method. Of course, we can use the green function, but we have seen that before. It's actually the same. We will study this time the singularities approach. In fact, this is the preconized method because this is far faster than the green solution. So, for the singularities method, just a reminder, you have this wind tunnel boundary discretized on several panels. At the center of each panel, you will add circulation singularity, and you have to verify that the normal velocity at each control point will be 0. So the resulting streamline lying at the server plane will never penetrate the wind tunnel boundary, which is a physics boundary condition. So we have two options. Velocity potential is as before. We can choose it or not. Normally we don't select that because we don't need that for vortex track prediction. So let's go try to select action. Select action, we have view the clipped wake. That's something we have did before. That's basically the input that has been clipped in order to retain the wake only. Then we have visualized the tunnel walls. And the third step of this procedure is quite straightforward procedure, is to solve the Poisson equation on the entire tunnel section. Basically, what it does, as you can see here, there's a sort of discretization along these tunnel walls, and this discretization will generate a sort of background uniform mesh, and we will solve the Poisson equation on that mesh very fast. So let's go for it. As you can see, if I change surface to surface with edges, you will see the background mesh that occupies the entire wind tunnel cross section. And each point of that mesh, we have solved the Poisson equation. You may increase that a little bit more and try it. Yes. As you can see, I use a coarse baseline mesh just to make sure that the constant values of the stream function actually follow the wall, the boundaries. This means that the amount of phases that I'm using here are enough to ensure that the streamline limit very, very close to the wall actually follows the wall. You will see that this contour line, as it gets closer to the wall, will follow better and better the surface. Of course, if my baseline mesh is coarse, it will not follow that better. So with 20 points, usually it's okay, as long as the vorticity region be here at the middle. So I let it as it is. Now I'm happy with these contour lines of the stream function. And I can tackle the next step, the next and final step, that's to solve the Poisson equation on the entire wake. So let's go for it. It's far faster than the case of the Poisson equation. And you can see it has taken just some few seconds, 7 seconds in my computer. So I tend to use this tool, the singularities method, even for free air. In that case, I put the walls very, very far from the object because this is very, very fast. I don't have to wait 7, 10, 15 minutes to use when I use the green functions. And it provides very accurate values. So sometimes in some versions of ParaView, as you can see here, you have the Poisson function, it's 0. As you can see, there are no values. I will take away the surface. There are no values of stream function. That's because internally there is a solver of linear equations that is prone to errors. That's something is out of our control. We cannot modify that, unfortunately. So you simply have to relaunch this solver, change a little bit the amount of points, let's say 2021. And with some iterations, it will find out a solution without diverging the internal Python solver. And voila, that's the case. You can see I started to 20, it hasn't worked. I changed that to 21, I relaunched that very rapidly. In 7 seconds it has computed, and now I have my stream function at each point inside the wake. Of course, I also have the vorticity inside the wake, and the product of both fields will give me the vortex drag density, like here, masked vortex drag as before. And this is the quantity that's actually being integrated. And in this case, I have 192 drag counts. If you remember, freer case was 270 or so. With the same level of vorticity, inside a wind tunnel, the effect of the constraint decreases the vortex drag. So this is quite useful to understand and to analyze the effect of the wind tunnel walls, and especially if you perform a wind tunnel testing to obtain the freer equivalent vortex drag, starting only from the vorticity that you measure at that plane. So that's all concerning Poisson Solver equation, and thanks for watching.